Before promises became native in Node.js, before async/await existed, before the ecosystem settled on a common pattern for async control flow, a developer named Solon McMahon had a problem. He was writing a lot of Node.js code, and he kept rewriting the same patterns: sequential execution, parallel execution, limited parallel, series with shared results. Every project. Over and over. So in 2010 he published a small library to NPM that collected all of these patterns into a clean API. The library was called Async. It became one of the most downloaded packages in the history of NPM. At its peak it was downloaded millions of times per week. For years it was effectively required knowledge for Node.js development. Understanding it matters even today, for two reasons. First, you will encounter it in existing codebases. A huge amount of Node.js code was written between 2010 and 2018, and a significant portion of it uses async. Second, the functions it provides map directly to the patterns we've been building manually, so seeing them expressed cleanly reveals the underlying structure. The core of the library covers three scenarios. Async.series runs an array of functions one at a time, waiting for each to complete before starting the next, and collects all results into an array. Async.parallel fires all functions simultaneously and collects their results when all have finished. Fail fast on any error, just like promise.all. Async.eachLimit processes a collection with a bounded number of concurrent operations. It's the task queue pattern, built-in and battle-tested. The argument order and callback conventions follow the same error-first pattern as Node.js itself. Once you know one async function, you understand the contract for all of them. Let's make the async library concrete. You're writing the web spider from this chapter. You need to first create the directory, then download the page, then save the file. These steps must happen in order. In raw callbacks, this is 3 levels of nesting. With async.series, it's a flat array of functions followed by a single completion callback. Each function in the array receives a done callback. Call done, with no error to proceed to the next step. Call done, error, to short-circuit the whole series. When all steps complete, the final callback receives an array containing the result passed to each done call. Now suppose you have a list of 100 URLs to check in parallel. You want all of them in flight simultaneously. With async.parallel, you pass an array of task functions and get back an array of results when they all complete. If any task fails, the completion callback fires immediately with that error and results from other tasks are discarded. This is efficient and its behavior mirrors promise.all exactly. But 100 simultaneous HTTP requests is too many. You want at most 5 at a time. Async.eachLimit is your tool. You pass the array of URLs, the concurrency limit 5, and an iterative function that processes each URL. Internally, async.eachLimit manages a pool. It starts 5 operations immediately, and as each finishes, it pulls the next URL from the list. The completion callback fires when every URL has been processed. The practical impact of the write concurrency limit is measurable. Processing 100 URLs with a limit of 5 takes approximately 20 times the time of a single request. Without any limit, you'd get rate limited by the target server. The right number is always found empirically. Test against your actual target, watch for errors, and tune. The chapter ends with a statement that might feel anticlimactic given everything you've learned. Callbacks, used with discipline, are sufficient for building production-quality asynchronous systems. This isn't nostalgia. It's a precision point. By the end of this chapter, you've seen sequential execution, sequential iteration, parallel execution, and limited parallel execution all implemented cleanly with callbacks. The code is readable. It's testable. It handles errors correctly. It doesn't need promises or async/await to be correct or maintainable. The authors make this argument deliberately. Understanding how to structure callback-based code gives you a foundation that no abstraction can replace. When you use promises, you're still creating asynchronous chains. You're just using the promise API to manage the callbacks under the hood. When you use async/await, you're still writing sequential code that awaits asynchronous operations. You're just using syntax that hides the promise machinery. The mental models from this chapter: sequential chains, parallel firing with a counter, bounded queues. Those models apply whether you're writing callbacks, promises, async/await, or streams. They're not syntax. They're logic. Developers who jump straight to async/await without understanding callbacks sometimes struggle when things go wrong. They don't understand why their code behaves unexpectedly, because they don't have the underlying mental model of what's actually happening in the event loop. This chapter built that model. The next chapter, on promises and async/await, will show you how modern JavaScript syntax makes the patterns cleaner, but the patterns themselves are what you'll carry forward for the rest of your career.